Our session today, we're going to learn how to use these statistical tables. These statistical tables are very important to understand our normal distribution, to understand our hypothesis testing, to as well understand our estimation. Okay, normal distributions is very important in that it helps us understand what happens under the probability distribution function. So it's one of the probability distributions, which is also called the Gaussian distribution. Okay, it is a distribution that has the following assumption that it is symmetric around the mean. It has a bell shape. It is defined by mu at the center, and the standard deviation simply measures the spread. So what you are able to see right now is a normal distribution here. So this normal distribution is the assumption that it is asymmetric. Asymmetrical means that the left-hand side is the same as the right-hand side. Okay, so the characteristics, the bell-shaped, the mean usually at the middle, standard deviation, there's the spread. This is 50% and this is 50% on the other side. Our normal distribution looks like. So symmetric about the mean, the mode, and the median are the same. They're here at the center. Then we have about 68% that lies within one standard deviation. So between here and here, this is 68%. Okay, so one standard deviation has about 68%. Two standard deviations, three standard deviations at most. So these are just key characteristics of this distribution. So two standard deviations are at 95%, and three standard deviations are at 99.7%. 99.7%. Right. So the normal distribution looks just like that. So now how do we read this normal distribution? We read it again as follows. So if we're given a normal distribution to read, we would have, let me get an extract from the table there. So if you're asked to read 1.20, 1.23, you go under 1.2 in this column, then 0.03 in the other column here where they meet. So the reading here is what? 0.8907. 0.8907. Okay, can somebody help me? What is the reading of 1.96? The reading of 1.96. Where do we go? 1.96 and 0, at 1.9 and 0.06 where they meet here. So what you're getting here is what? 0.9750. So you could as well do the opposite. If I asked you what is a Z of 0.9750, you just go backwards. 1.96 and you add the 0.06 collectively, it will give you 1.96. So if I asked you to give me what is the Z for 9131, who wants to try? We'll go in reverse. 0.9131. Z will be what? Go here, 1.3, top 6. So it's 1.36, right? That is how it goes. So these readings are very important for so many things that I'm yet to tell you. Sometimes you may not find the exact figure, but you get the closest possible figure. So 9.800, what we do, we look at here, 1.800. So here we have this one, 98.03, and here 97.98. So one is up by 3 and one is below by 2. So which one is closer between these two? Which is this one here, 2.05. So you pick the closest possible, 2.05. Are we together? But there comes a challenge when you are dealing with something that is equidistant. For instance, 95% or 0.9500. So let's look for it inside here. So 0.9500. So you discover this one is more by 5 units and this one is less by 5 units. What we do, we pick the smallest one and add a 0.5 at the end. So this becomes 1.645. 1.645, which is equidistant. You pick the smallest and just add a 5 at the end in short. So the readings are very important in our Z score distributions because they help us understand how to standardize. So the standardization formula for Z is given by Z is equal to X minus mean over standard deviation. All right. So if, for instance, you're given your mean as 10 and your standard deviation as 3. So we want to standardize the values as follows. Maybe standardize X is equal to what? X is equal to 10. X is equal to 13. Want to standardize X is equal to 16. X is equal to 6. So now these values of X, it's like you're using the US dollar. You notice that our Z values only end up of 3 point something. We don't have these values like 13 needs to standardize them. All right. In short, convert them to what we can read. The numbers that you are seeing here are equivalent to probabilities. They're starting from 0. For instance, if I were to tell you 2.0 here, means that the reading from here up to 2, 0 is here, 2 is here. So 2.0, the reading from this starting point up to 2, or this area, is equivalent to 0.9772. So it means that this whole region here is about 97%, 0.9772. All right. So meaning the remaining area here that is not shaded, we just subtract 1 minus that. You get the remainder. So I'll get to that later on, but I want you to learn how to do the readings. So how do you standardize the 13? Z is equal to what? X minus what? X minus mean over standard deviation. So our X is what? 13. So 13 minus our mean. Mean is what? 10. Given 13 minus 10 over 3. So it will be 3 over 3, which is 1. So meaning the reading is simply at 1 there. 1. That is 0.8413. I'm just interested in the Z. Here 16 minus 10 over 3. So 6 minus 10 is 6. 16 minus 10 is 6. 6 over 3 is 2. So this is the reading at 2.0. We get 0.9772. If we're dealing with 6, 6 minus 10 is 4. Minus negative 4 over 3, we get negative what? 1.33. So you always read to the nearest two decimal places here. If we had 1.666, you just read it as 1.67 and you read those. So can somebody help me? What is the reading for 1.33? You go to 1.3 here and 0.03 there. So the reading will be what? 9082. So this is a document that distinguishes every statistician from others. You're able to interpret the figures and what they mean. All right. Are we moving together so far? Any questions before I proceed? Are we following? Okay. So if you're following, now we need to do the real stuff. Because if you don't understand what I'm doing right now, what I'm going to do, you may not understand. Are we together? Are we following? So that this is how we do the reading. Now, let's go to interpreting these same Z figures. Which I said the readings that you're seeing there are mere probabilities under the graph. So you must understand that greater means to the right. So I'll teach you a formula called ISA, which gives you 4 steps that are important when you're doing normal distribution. You need to learn how to illustrate, how to shade, how to standardize, and how to apply the principles I'll teach you. So we call this ISA. So what is this uh, reading telling you? Just telling you 3 things. Number one, just telling you that you put a figure there. Z is greater than what? Greater than 2. So what 2 things can you tell me? Number one, the shading is big. Big shading. So when you have a big shading here, you read it directly because all these figures are cumulative. So whenever we're shading, we shade to the right because of the sign greater. Greater means shade to the what? The right. And a big reading means what? You read direct. So 2.0, if you're going to read it here, we just read it direct. This would be what? 0.9772. Just read it direct. 0.9772. Which is point number one. Point number two, suppose, oh, this is negative. So x is greater than negative 2. So whether you're on the negative on the right side, the bottom line is that the shading we're looking at is what? It's big. Okay, it's big. Suppose we looked at The same -2. Our zero is here. We have -2, as I said there. And the shading that is showing there is a small shading. Tell me any five things that you can tell me about this polygon. Number one, the shading is what? Small. The interested part we're looking for is small. Number two, the interpretation of this shading is Z is what? Less than. Negative what? 2. Why are we using less than? Because this sign is telling us what? To the left. Less than is to the left. So whether we are subtracting from 1, reading direct, it doesn't matter whether it's to the left or to the right. What matters is how big it is. So this shading here, we're going to subtract 1 minus 0. What? 9772. Why are we subtracting? Because the shading is what? Small. The shading is small. Okay. Is that clear? So this is on the left side. By dealing with the right side, can you tell me two things about this right side? We have a 2 there, positive, obviously. And it's shading to the right side. So what, can you tell me two things? Number one, the illustration is showing us what? Z is greater than what? 2. So this is to the right. However, since the shading is small, what are we going to do? We're going to subtract from 1. So 1 minus the reading of the probability, 0.9772. This is 1 minus 0.9772. Okay. What else can you tell me about this? Reading is small, which shading to the left. All right. So without being said, we can um, go to a question. Are we together so far? We're following. So if we're given our mean as 10, our standard deviation as 3. So find x is greater than 16. So we're going to apply ISA here. Number one, 0 is in the middle here. So the mean 16 want to standardize it. Okay. So our mean is what? Was given as 10. So why is 16? We need to identify 16 is on the right of 10. So how do we standardize 16? Z minus x. So 16 minus 10 is 6. 6 over 3 is 2. So this 16, when you rebase it, it's equivalent to 2. Then the sign here is greater, so we're shading this part here. Then to get the reading for this one, we have illustrated, we have shaded, we have standardized. How do you standardize 16 minus 10 over 2? Let me apply. So if the shading is small, we subtract from 1. So 0.9772. So that is the reading that we're going to have there. Okay. Suppose they've asked us to find the probability that what? That x is less than 3. What is the probability that x is less than 3? So we use ISA. We illustrate. We standardize. So we know 0 is always here. Okay. Then this is equivalent to 10. Well, that is our mean that we've been given. So 3 is on the left side of 10. So we need to standardize this 3. Alright, to standardize, the formula for standardizing is Z is equal to X minus mean over standard deviation. So here we have our X, which is what? 3, minus a mean, which is 10 over 3. So 10 over 7 over 3, it will be what? 2.33. So 2.33 negative just tells you that you're on the left side. But 2.33 is simply giving us the standard figure of Z here. The 3 is given to 2.33. But since the figure is telling us less than, all the figures in the table here are cumulative, they're more than 50. So this small figure here can't be more than 50. If you go 2.33, okay, I just cut the table there. Or suppose it was 2.33, 98%, we would subtract from 1. All right, so we'll continue on this later. I have another session now. I'll send you a video on normal distribution, then we'll look at exam papers on that.